This is question number 18 from 2013 biochemistry question paper. So this question states that you have expressed the following protein that has an isoelectric point of 6 and the best order of protein purification methodologies to obtain a pure protein is. Okay, and this is the diagram of the protein which they have given. Okay, this is a protein. So this is the gene protein of interest, and here at the N terminal this sequence is attached, which is a tag, and this is 6 histidine residue, that is called a histidine tag. Okay, so this is the question which we have, that states that you have expressed the following protein that has the isoelectric point of 6 and the best order of protein purification methodologies to obtain a pure protein. So this protein is N-terminally tagged with a histidine tag. Okay, so what are the different techniques of protein purification? So seeing this protein, which technique you think that best suitable for the protein purification? So this nickel, this binds where? This nickel. What exactly happens in this nickel affinity chromatography? Okay, so as it is shown in the image that this protein is tagged with histidine, right? So this nickel affinity chromatography technique, here we used a resin called nickel NTA resin, and this nickel NTA can bind to this histidine tag. Okay, this can bind to this histidine tag. So if in a column you have several proteins, right, many proteins, and the protein which will harbor this tag, which is a histidine tag, and if you give many beads, that is nickel NTA beads, so all those nickel NTA beads will bind to this particular protein, and the remaining protein will be eluted out. Okay, so nickel will bind only to histidine. Okay, so once the binding happens, the scenario is like this: the non-bound proteins come out, okay, and the histidine tag protein only remains, that is bind with the resin. Okay, so that protein only remains, that binds with the nickel. So now in order to uh, elute this desired protein out of the column and remove it from the nickel, so what is done is imidazole is used. Okay, so this imidazole performs the competitive binding for nickel NTA. So as histidine has affinity to bind to nickel NTA, imidazole also have the affinity to bind to nickel NTA. So there comes the competitive binding. So if you provide more concentration of imidazole here, so the protein will be removed, and this nickel will bind to the imidazole now, and then when you collect or when you take the elute, the free protein that is not bound to the nickel will be eluted out, and you can purify the histidine tag protein. Okay, so that is the basic principle, nickel affinity chromatography. So here in the question it has been asked the order of protein purification methodologies. Okay, so if we'll see all the 4 options, we can see only in the 2 options we have the option of nickel affinity chromatography. So other 2 options are automatically wrong. Okay, because if histidine tag is there, the best technique to use to purify the protein is the nickel affinity chromatography. Now out of these 2 we have to find out which one can be used. Okay, so here and the combination is same in the like nickel affinity chromatography, here also nickel anti chromatography and gel filtration chromatography, which is same in both. So gel filtration chromatography is the separation of protein based on the size of the protein. Okay, so the other thing is that here the ion exchange chromatography is mentioned in both. Two different. One it is mentioned cation exchange chromatography, another it is mentioned anion exchange chromatography. So first thing is, in the question also we have the isoelectric point of the protein, that is 6. So yes, when the net charge of protein is 0. Okay, so uh, that is the isoelectric point of the protein. Okay, so if so that is the pH at a pH at which the net charge is 0, that is called the isoelectric point of that protein. So at this pH, so pH 6 is the pi of this protein. So if you go above the isoelectric point of the protein, if you increase the pH above the isoelectric point, what will be the charge on the protein? It will be positive this side and negative this side, because at lower pH you have more free protons, right? Like lower pH more protons, higher pH lesser, okay, comparatively lesser. Okay, so if your protein is having, like at this point, if you see your protein like this, okay, this is what you assume at the isoelectric point, right? There will be net charge will be 0. So here, and so at this point, if you increase the pH, here what is happening, and deprotonation will takes place. Okay, here the deprotonation will takes place, and that's why the charge here it becomes like this. Okay, the deprotonation happens. Okay, so that is why negative charge appears. And at lower pH, when more uh, hydrogen ions are present, so here what will happen, something like this I can say. So this will take up the free protons from here. Okay, so that is why the charge becomes positive here. Okay, understood? So that is what happening. Okay, so at pH above pi, the protein remains in negative form, and pH below pi, the proteins remains in the positively charged form. Okay, so in the question they have given, in both we have the the pH which they are using is 9 and 8. Okay, which is higher than 6. So at pH 8 or 9, the protein is negatively charged. Okay, so if you want to purify a protein which is negatively charged, which chromatography you should use? Okay, anion or cation exchange, which one you should choose? So there is something other than pi, we have another thing that is called pka value. Okay, that is one thing. So that defines your basic or acidic amino acid. Okay, so for basic amino acid you have very high pka value. For acidic amino acid you have very low pka value. Okay, so for these basic proteins, either you have the charge uh, positive or neutral charge. For these acidic amino acid, because of the presence of charged residue, you can have a negative charge or a neutral charge. Okay, so that is why overall whatever this isoelectric point that has been calculated, it has been calculated for the entire protein, not only for the presence of the histidine tag. Okay, so whatever contribution of the net charge that comes all together of the entire amino acid residue side chain. So all together that is giving a charge to the protein, not only the histidine residues. Okay, so now comes this anion and cation. So on what basis they are named? If I am saying an anion exchange chromatography, what do you understand by that? Okay, if cation exchange or anion exchange. So very carefully you should understand the name. Okay, cation exchange, anion exchange, that means the exchange of anion is happening, that is why anion exchange. So if anion exchange is happening, the matrix is positively charged. Okay, the matrix is positively charged here, and when you provide certain proteins in this tube, okay, so suppose a positive charge, negative charge, double positive charge, negative charge, double negative charge, like this. So if you'll pass through all this protein in this matrix, what and initially what happens to maintain this matrix, some loosely uh, bound negatively charged, suppose chloride ion or something, is already bound here, okay, in low concentration. So when you provide the protein, what happens, the very first thing is, because this resin is positively charged, so positively charged proteins, this and this, they will not able to bind to the matrix. Okay, this will be eluted out very first because they won't be able to bind. Now comes, here comes what happens, there is a binding, a competition for the binding, so then the exchange happens. So this anion gets replaced by your protein. Okay, these anion gets replaced, so that is why the name is, next the scenario looks like this. The exchange of anion happens, so all the positively charged will come out and the negatively charged one will bind here. Okay, and these salts residues will also come out, or it will be washed off. So that is the exchange of anion is happening. So, and then further, now you have separated your protein based on the charge in comparison to other proteins, other positively charged protein. So if you have such a scenario where your impurities all are positively charged and your protein of interest is negatively charged, then it becomes very useful. So suppose only your protein of interest is negatively charged here, so other all the proteins will come out, and suppose this is your protein of interest, all if others are positively charged, only your protein of interest will remain bound to the matrix, and that can be further eluted out and will be giving you a purified protein, a pure protein without any impurities. So that is what happens in the anion exchange, and the vice versa happens in the cation exchange. So there the matrix is negatively charged and the exchange of cations takes place, so the positively charged protein is bound to the matrix. So if you want to purify a protein that is a negatively charged protein, if the protein is negative charge, that means you have to use anion exchange. If the protein is positively charged, that means you have to use cation exchange. That is the only basic logic here. Okay, so here in the prior case, at pH 8 or 9, if we have to perform the ion exchange chromatography, protein is present in negatively charged form, then you have to choose which chromatography, anion or cation. You will be using a anion exchange chromatography. So here, if we'll see the option, so B option states cation exchange chromatography. At pH 9, you cannot perform a cation exchange chromatography with this protein. Okay, if you want to purify cation exchange chromatography with this protein, you should have a pH lower than 6. If this would be 4 or something else, then this option would have been corrected. Otherwise, the correct option for this scenario is this one, which is the anion exchange chromatography at pH 8, and nickel affinity chromatography that can also be used for this purification, and gel filtration chromatography can be used because you have different sizes of the protein which you when you purify. So according to the size, you can separate the protein. So according to the question, the best scenario out of these four options is option C. and this is my NPTEL reference. Thank you.